Here's another example of using trigonometric substitution to solve an integral that involves a radical. Let's solve the integral of the square root of x squared minus 25 over x times dx. Now, as with the last example, we can't really simplify this integrand at all. This is kind of an ugly integrand. We can't simplify that root because we can't just take the square root of x squared to get x and the square root of 25 and get 5 and just call it x minus 5. That is not equal to the square root of x squared minus 25. You cannot distribute a root over subtraction. So there's no way to simplify this thing algebraically. But we can use trig substitution to turn this whole thing into a different integral involving trig functions that we do know how to solve. The first question is, what substitution should we do? We're going to want to write x equals some function of theta. But what function? Here's the rule of thumb. In general, if you're doing a trigonometric substitution problem, you're doing it because you see a root showing up in your integrand. Sometimes you won't always have a root showing up, but this is the general situation. If the root is of the form a number or number squared minus x squared, you'll want to use the substitution x equals a sine theta, where a is the square root of the first number that's appearing. If the number is a squared, then a is the square root of that. If your radical has x squared minus some other number squared, you'll want to use x equals a secant theta. And if your radical involves an x squared plus a squared, you'll want to use x equals a tangent theta. You can get away with using cosine, cosecant, or cotangent in these situations, but it will just be a waste of your time. Any situation where you could use cosine, you can just use sine, that will be easier. Any situation where you can use cosecant, you can use secant, and it will be easier, and so on. So you'll always want to use a sine, secant, or tangent, depending on what form your radical takes. And if you have other types of radicals showing up in here, then there are ways of handling that, but we'll talk about those later. Since our radical in this problem is a difference of two squares, we're having x squared minus a number squared under the square root, we want to use the secant version here. So secant theta. Now, if we just had x squared minus 1 squared, we would just let x equal secant theta. But instead, we have x squared minus 5 squared. 25 is 5 squared. So let's take that, the square root of 25, which is 5, and let's have 5 as the coefficient on the secant theta. And you'll see why this actually works in just a moment. Now's a good time to stop and review our 3 basic steps for trigonometric substitution. Our basic steps, first of all, choose which trig function you want to substitute in place of x. You'll usually use a number times sine theta, or a number times secant theta, or a number times tangent theta. And I've shown you which cases tell you to use which trig functions. If you make the wrong choice, you'll see pretty quickly that it's not working, and you can back up and try to make a different choice. So you'll choose the first trig function. You'll want to substitute every x that you see in your integral with that trig function, and don't forget your dx. Your dx is equal to some other function involving d theta. So you'll substitute that as well. And you should end up with an integral that's entirely in terms of theta. So next step, simplify that integral, and then solve it. And since you'll have an integral involving trig functions, you can use all the techniques we talked about in section 7.2, using trigonometric identities to modify the integral, using a u substitution usually to get that to work, and so on and so forth. Once you have that integral solved in terms of theta, your last step will be to replace those functions of theta back with functions of x. And generally speaking, when you're doing this, you may need to use a right triangle that represents the relationship between x and theta to help you replace various trig functions of theta with other functions of x. So back to our problem. We know that x equals 5 secant theta. That's the substitution we're going to do. Let's find our dx now. Dx is equal to the derivative of this function times d theta. So the derivative of 5 secant theta, well, the coefficient of 5 just goes along for the ride. And the derivative of secant theta is secant of theta times tangent of theta. And since we're doing this version of differentiation, we need to multiply by d theta. One more step that you can save until later, but let's do it now. I mentioned that in the final step of this, you'll want to use a right triangle to help you replace functions of theta with functions of x instead. But if you use that right triangle now, it can be pretty helpful. For one thing, it will help you to be certain that you've made the right choice of which trig function to substitute for x. And sometimes it will help you to make that substitution. So let's do it now. I'm going to draw a right triangle, just right here. Here's the right angle. Theta is one of the angles in that triangle. Usually you put it at the lower left, but it doesn't actually matter as long as it's one of the acute angles in that triangle. Now, x equals 5 secant theta. That means that x over 5 equals secant of theta. But secant theta is 1 over cosine theta. It's the reciprocal of cosine. So that is always, in terms of a triangle, that's always going to be the hypotenuse over the adjacent side, because cosine of theta is adjacent over hypotenuse. So let's use this fraction here to label 2 of the 3 sides. X will be the hypotenuse of the triangle, and 5 will be the adjacent side, the side of the triangle adjacent to the angle. Here is 5. Now we can use the Pythagorean theorem to work out what the final side is. We'll put a question mark here, and we know that 5 squared plus question mark squared equals x squared. If I solve for that question mark, we'll end up with x squared minus 5 squared, which is 25, and take the square root of that. So guess what? That square root of x squared minus 25, the same radical that is appearing in our integral, actually appears as one of the sides of this triangle. That is only going to happen if you make the correct choice of which trig function to substitute for x. So the fact that that same radical, the square root of x squared minus 25, is appearing in our right triangle is a clue that we have made the right choice of the substitution, and we are going to be successful here. So now, let's actually fill in our integral. We have a few choices for how to handle this. One option is we can say, well, the square root of x squared minus 25 divided by x in my integral, that is actually showing up as a ratio of 2 of the sides of the triangle. This is actually the opposite side divided by the hypotenuse. So I can cross that out, and I could say, well, that's actually the sine of theta. This is the sine of theta times dx, and dx is 5 secant theta times tangent of theta, d theta. Another option you have here is just to replace the x inside that root with 5 secant theta. I'll show you that option in a moment. These are 2 different options for making your substitution and then simplifying, and it's up to you which one you find easier to do. Since we have this here, let's now try and simplify this expression. Usually we don't want to have too many different trig functions showing up in our integral because they're hard to work with. In general, you want to have either sines and cosines together because they are compatible with each other, or tangents and secants together, or cotangents and cosecants. But in this situation, most of the time you'll find that you don't need to have cotangents and cosecants because you're not using those in the substitution in the first place. Let's pull that 5 that is our coefficient out front, and we have 5 times the integral of sine theta times secant theta, but perhaps I'll rewrite that. Secant theta is 1 over cosine theta times tangent of theta, d theta. Now I still have a tangent theta here. I could replace tangent theta with sine theta over cosine theta, but instead I'm noticing that I already have a sine theta times 1 over cosine theta. I could replace this expression right here with tangent theta. So actually my integral is the integral of 5 times the integral of tangent squared theta, d theta. And we can carry on solving this in just a moment, but I want to show you the other way that we can make our substitution here. So sometimes your integrand includes a ratio that is very clearly a ratio of two sides of your right triangle. And right away, you can pull out the appropriate trig function of theta like we did just now. We saw that we had the opposite side divided by the hypotenuse as the ratio that appears in our integrand. And we know that is equal to sine of theta, so we used that. Sometimes it's not so obvious, so instead, let's try this a different way. Instead, let's recall one of our trigonometric identities, one of our Pythagorean identities, which says that tangent squared theta plus 1 is equal to secant squared theta. You get this identity by starting with the original one, sine squared theta plus cosine squared theta equals 1, and dividing both sides by cosine squared theta. You end up with this one. Now, why is this useful? Well, you'll see. This integral is equal to the integral of, let's fill in our x squared. Our x is 5 secant theta. That whole thing is being squared. Minus 25, all under the square root, all divided by 5 secant theta. And our dx is 5 secant theta tangent theta d theta. So just to get some things out of the way, maybe I'll cancel as much as I can right away. I've got a 5 on the top and a 5 on the bottom I can cancel. I've got a secant on the top and a secant on the bottom I can cancel. I'll get rid of those. In the meantime, what have I got? The integral of, well, let's see. My integral of the square root of, 5 secant theta squared, that is 25 secant squared theta minus 25. But before I actually go on with this, maybe I'll actually factor out that 25. So we actually have 25 times secant squared theta minus 1, all under the square root. We're not dividing by anything else anymore, we're dividing by 1. This is still times tangent of theta d theta. But what is secant squared theta minus 1? Well, if I take my Pythagorean identity, tangent squared theta is equal to secant squared theta minus 1. So I can actually replace this guy here with tangent squared theta. And now that my root is in the form of a product of several things under the root, now I can actually take the square root of each of those things. I have the integral of the square root of 25, that's 5, times the square root of tangent squared theta, which is just tangent theta, times tangent theta d theta, and I end up with tangent squared theta times 5, again in my integrand. So either way that you do this, whether you decide to plug in the trig function into x into that root and then simplify it, which will always be successful if you've made the right choice of your substitution, then you will always be able to use a Pythagorean identity to simplify that root until eventually there is no root at all. And then you can just cancel and combine like terms and do all other things you can do to simplify this integrand. Or you can use your right triangle to figure out what ratio of sides of the triangle is already showing up in your integral and pick the right trig function of theta anyway. And in either case, you should end up simplifying your integrand and getting the same expression involving trig functions, no matter which method you use. So now we're ready to move on to step 2, which is simplifying our integrand. We've already done that. And now computing the integral. And we can use whatever techniques from section 7.2 we need to solve this. So the usual technique for integrals involving tangent and secant is to figure out which of those two has an even power. Now, it's a little bit tricky here because there's actually no secants showing up, but technically we have secant to the 0 power, which is an even power. And the hint here is we should actually keep using that same trigonometric identity, that tangent squared theta plus 1 equals secant squared theta, and rewrite our tangent squared theta as, well, here's 5 times the integral of secant squared theta minus 1. times d theta. Why is this useful? Well, we don't know what the antiderivative of tangent squared theta is. But we do know what the antiderivative of secant squared theta is, because that's just tangent theta. So in solving these problems, it's really helpful to remember, number one, what are the derivatives of trig functions, and therefore be able to recognize what the antiderivatives of those results are. And it's helpful to know your trigonometric identities pretty well, and you'll probably use the same identity multiple times in a problem. In this case, we've already used the identity tangent squared theta plus 1 equals secant squared theta twice. We may use it another time in this problem, so just keep that in mind and don't forget it. Now we're ready to find the antiderivative here. This is pretty easy. We have 5 times the antiderivative of secant squared theta. That's just tangent theta. We already know that. Minus the antiderivative of 1, which is theta. Don't forget that our variable here is theta. The d theta here is telling us that the variable is theta. And so the antiderivative of 1 is theta and not x or u or any of those things. It's theta, and that matters. And of course, we have an indefinite integral again, so let's add our constant, our plus c. Now we're ready for our final step, which is to replace all of our functions of theta back with functions of x. So how do we do this? Let's look first at our triangle. What is the tangent of theta? Well, that's pretty easy to figure out. Tangent of theta is always opposite over adjacent, and we know that our opposite over adjacent is the square root of x squared minus 25 all over the adjacent side, which is 5. So we have 5. I'm going to distribute this 5 in here as we go. So we've got 5 times tangent theta, which is the square root of x squared minus 25 all over 5. Those 5's cancel out, which is handy. Minus theta. Now, what is theta? Well, to figure out what theta is, I'm going to erase this triangle and all this stuff so I have room. And I'm going to go back and look at my original substitution that I did. X equals 5 secant theta. We just need to solve for theta. So let's divide by 5. X over 5 equals secant of theta. And what is theta? Well, we just need to undo the secant function. And by definition, the function that undoes the secant is the inverse secant, or arcsecant. Secant to the minus 1 of x over 5 equals theta, or you can say arcsecant of x over 5 equals theta. I prefer the arcsecant terminology here because I think that negative 1 looks like an exponent even though it's not an exponent, and it might lead you to use it incorrectly. So I prefer to write arcsecant, arcsine, arctosine, etc., when I can. But in any case, however you call it, these two functions are the same. They are the function that undoes the secant. So we're ready to go. Theta is just arcsecant of x over 5. Now, we need to multiply that 5 in. I wanted to multiply it in, so we've got 5 here, and then plus a constant, as always. Now, that 5 that's on the outside of the arcsecant and the 5 that the x is being divided by do not cancel, because you cannot bring the 5 inside the inverse trig function. It doesn't work that way. So don't be tempted to cancel those things. In fact, this is pretty much as simplified as we're going to get. So here is our solution right here. The square root of x squared minus 25 minus 5 times the inverse secant of x over 5 plus a constant.